to prepare for to learn how to prepare for the moon and Mars. Uh, so this talk is about looking for places on the Earth that are similar to the moon, to Mars, and places beyond, so that we can practice to the extent possible and prepare ourselves for the journey. Famous explorers have always said that expeditions are won before you even go onto them. They're won in the planning stage. So if you plan things meticulously, your odds of succeeding are much better. Uh, so let me move on with this. So Mars, why Mars? Well, because it's the planet next door. Venus is a bad idea to send people there. I mean, it's a very interesting world, but temperature at the surface of Venus is that of a pizza oven while it's baking pizza. So Mars is a lot more welcoming from that perspective, but it's still a pretty harsh place. I'll talk to you about the possibility of one day humans going to the outer solar system as well, in particular to Titan.
From what
Which
I've
is an
heard,
planet.
in order for Mars to be livable, we would have to make climate change happen there, and it would take tens of thousands of years.
Yeah, and making a planet habitable is only one. It's in my view, is not even a realistic option. Okay, I mean, I'm talking about the short term, going to explore these places. What we do with these worlds, I get the sense that we'll achieve interstellar travel before we get around to having even the capability of terraforming any one of these planets. Okay, so anyway, that's a bigger discussion. So Mars is a fascinating place. This is the Earth, Moon, and Mars compared in size. So Mars is intermediate between the Earth and the Moon. Gravity on the Moon is 6 times less than what it is on Earth. So you would have a felt weight of 5 times, of 6 times less than on Earth if you were on the Moon. Whereas on Mars, it's roughly a third of Earth's gravity. Okay. Now, this is actually a Martian landscape from Curiosity. And there are a few good things that are working for you if you want to send people to Mars. The 24-hour day almost. It's 24 hours and 37 minutes. I don't know about you, but I could use 37 minutes more each day to wrap things up. There's plenty of water on Mars. NASA announces the discovery of water on Mars every year. That's mostly to encourage funding. There's plenty of water on Mars. We know that. We've known that for decades. There's water in the atmosphere. There's water in the ground in the form of ice. And there might even be liquid water in some pockets near the surface and deeper down for sure on Mars today. There are plenty of minerals and the regolith. The regolith is the soil, if you will. And of course, we talked about the gravity already. Now, on the right, I've listed for you the things that will kill you if you were to venture onto the surface of Mars unprotected by a spacesuit or a habitat. Okay, so the first thing that will kill you is the low atmospheric pressure. Your blood would boil. All the gases that are dissolved in your bloodstream would fizz, would bubble up, and you would die of violent decompression, basically, if you were exposed to the Martian thin atmosphere. And so you need a spacesuit to remain pressurized so that the gases that are dissolved in your bloodstream stay dissolved and are not in the form of gas bubbles. So that will kill you in seconds. And if that didn't kill you, then the fact that the atmosphere is unbreathable will kill you within minutes. You need oxygen, and there's no free oxygen, O2, in the Martian atmosphere to speak of. If that didn't kill you in minutes, well, then the temperatures would kill you within a few hours. And so temperatures on Mars on average minus 80 degrees Fahrenheit, so that's really cold. If that didn't kill you, then the dust, which is actually toxic, which is in part why the movie and the book The Martian don't work. If you ingest this dust, it contains perchlorates and peroxides. Those are actually toxic for you. You would die within a matter of a few days to weeks. And then finally, the radiation at the surface of Mars is expected to be lethal over the course of years of exposure if you were on Mars. Interestingly, it's not the thing that will kill you the soonest, but it's the thing that will kill you the surest, because there's very little we can do to protect ourselves from that other than being buried, either in sandbags or in a subterranean shelter. Okay. All right. So why would we even want to do this? Well, we want to go to Mars because we're looking for life. And I think what's often not specified enough is that we are looking for alien life. We want to find a form of life on Mars that is not of the Earth. All life forms on Earth are related genetically. This is on the left or in the middle here. The tree of life on Earth, it shows you all the three domains of life, the bacteria, the archaea, the eukaryotes. We are a eukaryote, in case you were curious. In other words, we have cells with nuclei, and we have DNA inside these nuclei. But these other forms of life also have genetic signatures, and we are all apparently related, which is easiest interpreted as being due to the fact that we spring from a common ancestor that has now disappeared from the fossil record because it's way back to the earliest history of the Earth, of which we don't have a good geologic record anymore. But what we're looking for on Mars is something that would not plot into this family tree of life on Earth. And we want to find something that is genetically alien to us, not just us humans, but us life on Earth. And for that to be possible, for you to be able to determine that you found alien life, you have to be able to do genetics on it. And to do genetics on it, you have to find it alive, essentially, or dead for not long time at all. That's a big challenge because we don't think that anything can be living at the surface of Mars today. Okay, the environment there is too harsh. Anyway, we've landed in a bunch of places, 17 more or less successful landings. 10 were American. So this is quite a presence of ours. And pretty much all our missions to the surface of Mars have been huge successes. This is one of my favorite sites, the first place where we landed and where we actually looked for life that was still alive. The results were negative to, at best, ambiguous. But hopefully we'll have more missions that are looking for living life than just fossil life on Mars in the future. We've also sent rovers.
So,
yeah.
so with the perchlorate and peroxide soil, like in the future, would colonists be able to actually use that soil both as would it be more useful to the colonists just as a chemical feedstock because of those chemicals rather than like using it as a substrate to grow crops in?
Yeah.
And talking long term.
That's a good question. So the answer is, the good news is that the peroxides and the perchlorates can be washed out if you run them through running water, which you can, produce or even bring to Mars, but there's plenty of water on Mars. So you can, if you flush out your soil, if you clean your soil substrate of perchlorates and peroxides, you can then grow stuff in them that would not be toxic. The other good news is that these perchlorates and peroxides, if you also save them, they can be used as rocket fuel. We actually have some rockets on Earth that use perchlorates as a...
Yeah, that was what I was going to ask.
Mhm.
That sounds like a really useful thing if
Yeah.
you're trying to get something to get off of Mars rather than like either slowly like ripping apart like carbon dioxide from the
Yeah.
atmosphere, or having to electrolyze water, like a huge amount of water using a huge amount of power from the sun, right?
Yeah.
That it sounds a lot more like, as an oxidizer, it sounds like a lot easier to obtain of a fuel source,
Yeah.
right?
You're right. It's readily available. On the other hand, a lot of these assumptions about how we could extract water or break down carbon dioxide assume that we will have endless power on Mars, not just solar power, but nuclear power as well. So if that were the case, it might ultimately be more practical to synthesize some of this stuff and to just wash the perchlorates out, as opposed to I mean, well, you'd still have to extract the perchlorates, and that's not going to be easy without water. But anyway, those are very good points. Your name is WC? Is that
Will? Yeah, Will.
Bill? Okay, good, Bill. Thank you. Good point.
Let's try not to interrupt Pascal and save our questions to the end, or at least put them in the chat if you just can't hold them.
That was a very good point. I mean, these were all good points. So anyway, just a few more picks. This is one of my favorites. It's the Perseverance site. I mean, look at this. It's almost like you're in the desert on Earth. And in fact, the guy who processed this image put a little added Matt Damon there at the top of the butte, just to provide scale. But of course, the guy's not there. This is on Mars. Okay. But so far, no sign of life, and that's an important thing. Not even fossil forms of life. We're looking, but in any case, we don't think we'll find living life anywhere near the surface of Mars today. Which means that I think in the future, the search for life to find living life, so that you can do genetics on it, so that you can prove that it's alien, if it were, you have to go underground. And so there are two ways to go underground on Mars. You either drill, that's shown on the right, it's sort of the hard way, or you find natural caves, especially caves in places that might still be warm, like volcanoes. And we know of caves on the flanks of some of Mars's giant volcanoes. Okay, so here are 4 of Mars's giant volcanoes, which you might be familiar with. Everybody knows, I think, Olympus Mons. But for example, on Arsia Mons at the lower right, there's this gigantic cave opening called the Jan Pit. And this thing is 150 meters wide, over 175 meters deep. It's actually one of these pits that's so deep that we can't even see the bottom by enhancing the pictures. Sometimes when you see a pit like this, you enhance the pictures, you can see sand dunes rippling at the bottom. Here we see nothing. It's a bottomless pit on Mars. Anyway, we think that these are the types of caverns that could be an incredible opportunity for life to eke a living on Mars even today in a living form, because it would be shielded from radiation, buffered from stark temperature variations day and night. So the temperatures in the cave are more even. That's why we keep wine in cellars and cheese as well, because the temperature on the ground is more even. Places like this would also be shielded from micrometeorites, and you could have warmth and even water vapor being emitted by your volcano if it's still even a little bit active. And so this could be a really cozy nook for life if it were present on Mars. And so I'm a big advocate for us going to explore caves on Mars in the future. So how will we explore Mars? Well, this is where we go to these extreme places on Earth to find this or that aspect that is similar to Mars. Of course, no place on Earth is really like Mars. No place is as cold. No place has Martian gravity. But one place that we've been going to is Devon Island in the Arctic. And Devon is the largest uninhabited island on Earth. It's about the size of West Virginia. And on it, you have this giant meteorite impact crater called HAUGHTON crater. It formed, that's the name of our project. We go up there every summer, the HAUGHTON Mars project. It's named after this meteorite impact crater, HAUGHTON crater. And HAUGHTON crater formed 21 million years ago, 23 million years ago, and it's about 20 kilometers in diameter. Okay, so this is a view of HAUGHTON crater. It looks like a bullseye in the landscape, seen from 10,000 feet of altitude. And I'm showing you the size of the impactor that could have created this crater if it had come in at a speed of about 20 kilometers per second. Okay, which is quite typical of the speed of an asteroid hit in the solar system here on Earth. And for scale, I've also put the Eiffel Tower there in the middle of the crater, to give you a sense of how big this thing is. So we have a base that's at the northwestern sort of rim of this crater called the HAUGHTON Mars Project Research Station. So this is what the landscape looks like. And it's really a true desert in the sense that there's no vegetation, no sagebrush, no what do you call these things, that no tumbleweeds, nothing. Okay, and you have ice in the ground and a rocky surface. This is Mars on Earth. Okay, now I won't go into a lot of geological details, but I'm going to show you a sequence of slides where you have Mars on the left and Devon Island on the right. just to show you the types of comparative studies we can do. So we can study how craters weather over time, and therefore what climate does to your surface. We can study features that are indicative of ice in the ground ice. We can look at glaciers, how they flow on Mars and also on Earth. We can look at rock glaciers. These are glaciers that have not just ice, but a lot of rock in them. We have both examples on Mars and on Devon. These are a special type of valley called sapping valleys, examples on Mars and on Devon. Valley networks, which are really bizarre on Mars, but we find some valleys with this bizarreness on Devon Island. Canyons are very similar in morphology here. Glacial valleys as well. So we think that Mars's valleys, some of them at least, were once occupied by glaciers. In fact, might have been carved out by glaciers. Here are other examples of that. And then a whole range of gullies. These are gullies of type 1 on Mars and on Devon, gullies of type 2, gullies of type 3, gullies of type 4. So I hope you get the sense of how incredible Devon Island is, because it's like a mini Mars on Earth, with differences, of course, but we think that they have so much in common for a really good fundamental reason, okay? And that is that a lot of these landscape features on Devon are the result of cold weather, cold climate, ice-rich processes, okay? Glaciers, glaciations, ice in the ground, rare presence of liquid water, etc. And then you've got the rocky landscape, okay? I mean, look at this. Look at this. You can't make this up. In fact, it's funny because if you go on the internet, some people think that we've actually never been to Mars, and all of this was filmed on Devon Island, which is really funny, because that's almost the best compliment you could make to us working at this site, is that some people think that NASA's faking Mars by just doing all these missions, so to speak, on Devon Island. Of course, NASA is going to Mars. It is not filmed on Devon Island, but I find it funny that they would think that the place is so Mars-like. Ancient lake beds, paleo lake beds, okay? Ancient lake beds, Mars on top, Devon Island on the bottom. And then there's also similarities with the moon. Here, Shackleton crater is a large crater, impact crater that's at the south pole of the moon, where NASA Artemis astronauts might go to. Well, it's just exactly the same size as Houghton crater. So we think that astronauts will one day come train at Houghton crater as part of their prep to go to the south pole of the moon. Here's some landscape, the moon versus Devon Island, okay? The topography, the terrain. Of course, now I show you the pictures in black and white so that it's more moon-like, but you can see that aside from the color and the bright blue sky, the terrain is actually quite similar, okay? We've got giant impact boulders. That's me and my dog. I take my dog to the Arctic every summer. He keeps an eye on polar bears. There are patches of ice as well, just like we think that in the shadowed, shielded parts of the moon's polar regions, there are ice patches as well. The terrain is very similar and conducive to exploration studies. And then, of course, we test robots, and we're looking at how humans will explore Mars and the moon in the future. Okay, so it's a training place for the future, but it's also a testing place. And so I don't have time to go over all our testing, but the spacesuit is one of the things that we test. Currently, the spacesuit weighs about 300 pounds, what you see there on the left. It was used on the space shuttle program. Now it's still used on the space station. That thing weighs 300 pounds. If you take that spacesuit to the moon, where gravity is 5 times less, 300 pounds divided by 5, that's 60 pounds, or 50 pounds. Sorry, gravity on the moon is 6 times less. So 300 pounds divided by 6, that's 50 pounds. 50 pounds, that's bearable. I mean, you can carry a backpack that's 50 pounds. You can still do field work, and that's why we can do field work on the moon. But if you were to take the same spacesuit, which is pretty nicely designed, I mean, it's already pretty lean and mean. If you take that same spacesuit to Mars, 300 pounds on Earth would have a felt weight on Mars of 125 pounds. So wearing that same spacesuit on Mars, you would feel like you're carrying a load of 125 pounds on your back. And that would really be difficult for you to do any field work in. So spacesuit engineers have a big challenge. We have to, and hopefully you guys can contribute to helping solve this challenge, which is to cut the mass of the spacesuit in half. Spacesuits on Earth cannot weigh more than 150 pounds, so that by the time we take them to Mars, they will have a felt weight of only 50 to 60 pounds or so. Okay, so that's a big challenge to cut the mass. I mean, we can shave off a few pounds here and there, but shaving off 150 pounds out of a 300-pound suit, that's a big challenge. Okay, so we don't have the solution to that yet, not entirely. And hopefully you guys, if you go into aerospace engineering or mechanical engineering, or you can help us come up with some solutions for this problem. Okay, so we've been working on it for the past 2 decades, trying to find ways to make the future Mars spacesuit lighter. And one idea is to offload some of the oxygen tanks, which are very heavy, some of the batteries, which are very heavy, some of the water tanks, which are very heavy, offload them from the spacesuit backpack onto some sort of a little rover that you can drive around. Okay, so we'll get back to that in a sec. Anyway, on top of that, your suit has to withstand dust storms. And so this is actually a painting I did of a dust storm, you know, racing across the Martian surface, about to engulf your little base. I mean, these types of dust storms really exist. This is a view of one from orbit on Mars. Okay, so they can be pretty. Now, of course, dust storms, unlike in the book and the movie The Martian, even though they can be fast in speed, the wind speeds can be high. The wind pressure that you feel would be very, very low because the air is so thin. Okay, it's a bit like standing on the Earth in the jet stream up in the stratosphere of the Earth. If you're facing the jet stream, which are these very fast air currents in the stratosphere of the Earth where the air is so thin, well, you would hardly feel a breeze. I mean, obviously you wouldn't be in a just bare skin, but still, if you, let's say you open your helmet visor for a bit, you would hardly feel a breeze because even though the winds are coming at you at 400 miles an hour, the air is so thin that you would feel hardly any pressure. So even in these big dust storms that we think we see on Mars, in fact, that we're sure we see on Mars, we also know that there's no way they would blow a guy over or satellite dish and hit something with it. I mean, you don't have enough dynamic pressure, it's what it's called. Pressure resulting from the speed of the wind to actually blow anything over. Okay, you would hardly feel a breeze. So anyway, dust storms do loft dust, and so we've done some studies. This is another form of going to an extreme environment where you go into a lab, you put on a spacesuit, and you essentially get hit by dust that's simulating Martian dust hitting the spacesuit. Okay, you won't get blown over, but the dust grains can still be coming at you at pretty high speeds, and so they could wear and tear your spacesuit. And sure enough, what I show you in black and white there on the lower right is spacesuit fabric getting dinged by little dust grains. Okay, that's spacesuit fabric from the Apollo era getting cratered, if you will, by little dust grains. Okay, and then of course we want a spacesuit to help you do some rock climbing because we've got canyons to explore on Mars. Okay, look at this canyon. This giant canyon that runs across Mars at its deepest is over 8 kilometers deep. So it's deeper than Mount Everest is high. Okay, it's incredible. And so we want a spacesuit that's going to be very capable to allow us to do all these things. And then now we know that not only are there caves on Mars, but there are plenty of caves on the moon. We know of over 300 caves on the moon. Here are some examples. These are pits in the ground. And I've actually found a few of these as well near the North Pole of the moon. And the ones at the North Pole are very exciting because, in fact, there's some at the South Pole too. These polar caves are quite exciting because they would never see the light of day. Sunlight would never enter these caves, and so they're going to be super cold, so cold that they could accumulate ice over time. Okay, one molecule of water bouncing around on the moon, getting trapped in a cave over eons. And so, wow, now not only would you have shelter on the moon, but you would have, you know, maybe some water ice sitting there waiting for you to harvest. Anyway, we want to understand how ice behaves inside caves, and so we go to Iceland for that. So this is another analog for you. This is a moon-like cave inside a volcanic lava flow on ice in Iceland. We've mapped it out. There, look at these giant masses of ice inside this cave, and we even flew a drone inside this cave to map it all out. And here's the result of our mapping. I mean, first of all, on the left, you can see how the top picture on the left is just showing you the aerial view of the drone of the entrance of the cave. So it's a hole in the ground. But then once we've mapped it out mapped out the cave with the drone, you can see how it stretches in two different directions, like a tube. In fact, it's a lava tube. It's a tube-shaped cave that stretches on either side of this circular entrance. Okay, so we would like to map out some of these caves on Mars in particular with drones in the future. And then, of course, we're looking at how humans might enter these caves and explore them. So we've seen astronauts in spacesuits exploring caves in science fiction movies since forever. But this is actually the first time, and it happened last year, the first time that a spacesuit manufacturer looked into caving for astronauts. And we did that in Oregon in last September. Okay, so these are pictures from a cave, a lava tube in Oregon. We're looking at where to put the lights. We figure we need some shielding to protect the astronaut from bumping their helmet visor against the walls of the cave. So we figure they're going to need some sort of a hockey goalie type of grill in front of their helmet visor that you can snap it on if you're in a cave, if you can take it off if you're not. But we need your help here, guys, to come up with other things that would enable humans to explore caves on Earth. And this is a view of what it might look like in the future. Okay. So, and then this summer I worked with Luke Landy to sort of go to the next step from what's shown here, which is to design some future tools for moon exploration and Mars down the road. So Luke gave you guys a great talk. I won't cover his material, but what he did was very, very timely, and hopefully we will turn some of these concepts into actual tools that will fly with the Artemis astronauts and future astronauts to the moon and Mars. I'm going to skip over this, even though that's super interesting. So this is what the Mars suit might look like in the future. All right. We also work on rovers, vehicles. So, for example, on Devon Island, we are testing ATVs. We think this is the best concept to make your spacesuit lighter. So you offload the batteries, the oxygen tanks, the water tanks onto your ATV. You recharge your backpack while you're driving. But then when you walk off of your ATV to go pick up rocks, for example, your ATV will follow you like they make suitcase do that now in airports. Okay, so it can follow you. It's a smart car. Okay, this is a two-seater, same idea. You can see that behind the seats, compared to the lunar rover, which had nothing much behind its seat, I mean, other than a tool rack, behind the seats of this rover, now you have oxygen tanks, water tanks, so that you can recharge the backpack as you drive, and therefore keep the backpack pretty light at any given time. Okay, that's one way to make the spacesuit lighter. For longer road trips, a pressurized rover. This is the RV approach. So we've been testing this concept with NASA in the Arizona desert. In fact, I was lucky to be one of the first scientist pilots to test drive this thing in the Arizona desert in 2008. It's an incredible machine. It can turn on a dime, not make a U-turn, as in flip around. The three wheel sets on each side can configure themselves into a sort of a giant circle, and you can just spin around the center of shape here, center of form of this thing, and drive out the other way. So in case you get dead-ended in some sort of a very rocky valley and you can't drive further, you don't even need room to make a U-turn. you can just spin around and get back out. So to figure out what it's going to be like to live and work inside a rover like this, possibly for weeks on end, driving across the moon or Mars, we use Humvees on Devon Island to simulate that. And to get Humvees, it's pretty to Devon Island, it's pretty epic. We wait for the Northwest Passage, which you see here. If you were trying to travel from the Atlantic, which is on the right, to the Pacific, which is on the left, you can see that, and you want to avoid ice, you can see that there's a seaway that sort of goes in from the right at the top there, and then you go sort of south from there, and then you go out west through the islands. Okay, that's the Northwest Passage. It's frozen most years still, but it's more and more navigable in the summer. And we waited for the winter for all of this to freeze over so that we could drive our Humvees across the sea ice to Devon Island. Okay, so Lynn mentioned earlier a movie that we did. Well, it's a documentary on this expedition to get one of our Humvees to Devon Island, where we drove it on sea ice for weeks to get it to Devon. That was pretty epic. And if you have nothing better to do, I suggest you watch that movie called Passage to Mars. Yes, here it is. Passage to Mars. I think it's on Amazon Video. And of course, down the road, we want to learn lessons. We have a base camp up on Devon Island, which I didn't show you, but from our experience there, we are hoping to help NASA design an optimal base on the moon eventually, and also a base on Mars down the road. I'm wrapping up here. Beyond Mars, to me, a very exciting target for humans. And of course, you know, we might all be long gone by the time this happens, although immortality is part of what's possible now in the scientific future. But anyway, Titan, one of the giant moons of Saturn, is a very attractive place. It has a very thick atmosphere. The atmosphere of Titan is 1.5 times thicker than the atmosphere of the Earth. And so you don't even need a pressure suit to be hiking around on Titan. All you need is to stay warm. It's very cold. Temperatures on Titan are around minus 180 Fahrenheit, I think, if I remember well. So super cold. And of course, the atmosphere is toxic. You need to protect yourself. But what we really need there is a very warm chemical suit, like the level A chemical suits that people, you know, use for when they're decontaminating a site, you know, in an oil spill, for example, as opposed to a real pressurized spacesuit, which is really required for the moon and Mars. So to some extent, getting humans to explore the surface of Titan is actually easier than the surface of Mars or the moon. Okay, the challenge, of course, is Titan is super far away. It's around Saturn, but once you get there, it's almost a friendly place. Okay, and so this is what we know of the surface of Titan. This is amazing imaging, descending under a parachute towards the surface of Titan. This is one of the last pictures during the descent imaging. You can see some valleys and some. The rock there is mostly water ice, which is sort of interesting. And then this is the landing spot. The little capsule came to a landing, and this is the landscape that it saw, and then it froze. But these little blocks are made of water ice mostly. Okay, so on a world that is so cold, water becomes the rock, the local rock. Okay, so this is very different from what was imagined in the 50s. This is actually a painting from the 1940s by Chesley Bonstell of what Titan might have looked like. So a lot of things are accurately done there, like, you know, the fact that you would see Saturn with the rings edge on. That's because Titan is in orbit around the equator of Saturn, of course. So all of this is correct, but what was off is the atmosphere. The atmosphere is actually, there is one, and it's very thick. So this is a painting I did showing how, you know, Saturn might just break through the clouds a little bit briefly, but otherwise you're engulfed in this organic haze on Titan most of your time. Okay, So anyway, with another high school student, not part of your program, but with another high school student, Jonas Diju, I worked on this concept for a Titan spacesuit. And it's not pressurized, but of course it has insulating layers, and the color blue was chosen because that's the complementary color to orange. So it's the most contrast giving color for an explorer on Titan. All right, thank you for allowing me to speak for so long, but I'm done.
Well, there's been a call in the chat to answer some questions. So if you're able to give us any extra time, I'm sure there are
Yeah,
some.
oh yeah, I can.
Maybe we should see if we can get people started on the Jamboard while we do a Q&A, and then people
Sure.
can do
Yeah,
their
so-
Jamboard and then leave if they have to go.
Okay, so very, very quickly, we have a Jamboard for you all. Has anyone used Jamboard before? You can nod or say yes in the chat. It's kind of like an online whiteboard.
Junior year.
You've used it in school. Yeah, since all of you went to COVID high school, I'm sure you use this tool. So there are 3 slides on the Jamboard, and the purpose is to gather feedback from you all on the meeting topics for tonight. So the mind mapping and then Pascal's talk, which I'm sure everybody loved. But also to understand how we can better support you in the future, because we're going to be doing these monthly meetings for hopefully a few years. So this is what the Jamboard looks like. I'm going to put a link in the chat. So you can navigate the Jamboard using this arrow to see the 3 different slides. So we're asking you to add a rose, which is a highlight, a success, or something positive from this evening. A thorn, so something that was challenging or something that you could use more support with or maybe didn't enjoy. And then a bud. So if you have any new ideas or something you're looking forward to or something you want us to focus on in the future, you can add that here. And to add a sticky note on the left-hand side, this button looks like a Post-it and it will pop up a sticky note. You click save and it'll come on the screen and you can move it around. So while Pascal's answering questions, if you all could put one thing on each slide, that would be incredible. Okay. I'm going to stop sharing.
Thank you so much for that talk. And I have to reiterate that I don't really know very much about planetary science, so I just love listening to all the stuff that you've been up to. It's just absolutely fascinating to me. And I think I wrote you a note after the last time I heard you talk about the concept of looking for life on Mars, where you're seeing alien DNA. It's not like our DNA. That whole point of the DNA differences had never occurred to me. You know, that we would know that it was truly alien life if it had like totally different kind of DNA.
Yeah.
I just find that really, really interesting to think about.
I mean, that's actually an interesting point, because right now we're focused on looking for signs of past life. And I sometimes tell my colleagues and NASA that, you know, we could be driving around with this rover and see giant bones sticking out of a road cut. And you still couldn't be sure that it's alien life that you found, because we know that Mars and Earth are not isolated. And we have meteorites, for example, that were kicked off of Mars by an asteroid or comet hitting Mars, and bits and pieces of Mars traveled through space. They fell on Earth. We picked them up. So it's conceivable that life was transported from Earth, was transported to Mars. We could have seeded Mars with Earth life. It could have picked up there, and we might end up with a creature on Mars that's actually related genetically to Earth life. So in which case, finding life on Mars would be exciting, of course. I mean, you know, we'd write a paper in a scientific journal, but it wouldn't be like finding alien life per se, because it would still have come from the same origin. So this genetic thing is really important to hammer in. Yeah.
Right. Yeah. I mean, the Mars and the Earth exchange chunks of rock on a fairly regular basis, right? So the only way you would really know that it didn't come from Earth if it was a totally different kind of DNA.
That's right. That's exactly it. Genetically different. Yeah, exactly.
I think
So-
another question.
So yeah, about like the challenges that are faced like with both Mars, but also like lunar expeditions as well. Like in particular, like that, the whole idea of the dust being one of the biggest like problems that you'd actually face, right?
Yep. Yep.
Because regolith will just shred your suit over
Yep.
over extended periods of time,
Yep.
right?
Yep. Yeah, that's a very good point. And in fact, you know, if you remember that slide where showing the, you know, the 5 things that will kill you on Mars, okay? When it came to the dust, I only brought up the fact that the dust could be toxic because it could contain perchlorates and peroxides. But I forgot to mention that the dust is also very abrasive, and will mechanically jam a lot of your mechanisms. So you're right. The secret to exploring the moon and Mars will be how you manage your dust, how you manage the dust. We're going to have to be very clever to brush off the dust before we enter any cabin, or somehow go into an airlock where once we brush off the dust, it gets sucked into, you know, and evacuated basically from your airlock before you go, you know, further into your vehicle, etc.
Isn't there also kind of a trade-off between like more maneuverability in terms of your suit and its ability to survive that continuous
Yeah.
abrasion as
Yeah.
well?
Yeah.
Like in theory, what you would want, because you can keep the temperature, you can just have a nice insulated suit and keep it like, and keep the temperature relatively within your so
Yeah.
that you don't have to have as much of a massive complex suit to support
Yeah.
your life.
In fact, to
You
your
can
point,
just,
you're absolutely
you can,
correct.
yeah.
To your point, we are actually advocating that spacewalks in spacesuits be kept relatively rare. And that's sort of a surprising recommendation, but it's understandable because of the point that you're making. You know, spacesuits are going to be needed for all kinds of things, of course, but you want to, because of this dust issue, you want to really minimize the use and the wear and tear of your suit, on your suit. And whenever you can explore by just saying inside your pressurized rover. So for example, the pressurized rover, if you noticed in one of the scenes, I had some robotic arms in the front, and like even a helmet bubble sticking out of the front of the rover. And the idea there is that you actually stay inside your rover as you drive around. You do drive-by geology. You don't necessarily have to go out on a spacewalk to pick up a rock. As you drive along, you can, just like in a submarine, you know, like a portable baby submarine, you can put your head in that bubble and you can see the rocks go by. And if you see something interesting, now you use robotic arms, you know, which are haptic. So you know, they do whatever you do with your own arms. You can pick up a sample, save it, and you don't have to inflict that wear and tear you were talking about on your spacesuit. And so now we're saying, let's save the spacewalks for all those times that are really critical or emergencies or even, you know, really necessary. The rest of the time, we should just stay inside the comfort of our vehicle.
I think the Artemis program has looked towards using like electrostatics to get
Yeah.
like electrostatic mesh inside of their suits, but it still only does so much because there's still some loss of durability due to the
Yeah.
regolith.
Yep. I actually worked with a high school student on a dust removal project. And the solution we came up with was essentially I mean, it's going to sound silly, but it was being in an airlock where you have a brush. So you're getting a bit like in a car wash. You have brushes that are essentially kicking off the dirt off of your suit while that dust is getting absorbed and sort of taken out of that airlock. It's still not going to be perfect. You're still going to be left with, you know, some dust, but it's a type of concept that we're going to have to implement, at least in the future, if we're going to do a lot of spacewalks. Yeah.
So we
I mean,
have
you
a
know,
couple of interesting questions in the chat from
yeah,
some of the other people.
yeah. All good points,
Presley,
though. Very
yeah,
good.
Presley wants to know, how does one get involved in missions like this, analog missions, and what kind of scientists do you normally work with? Are they astronomers or engineers or?
I that's actually part of why I enjoy this work so much. I get to work with both scientists and engineers. Uh, I mean, and in science, it's geologists, biologists, people who are specialized in life in extreme environments, people who are specialized in even the history of exploration sometimes. So, you know, anthropologists are part of the people that I collaborate with. And then on the engineering side, it's aerospace engineers, mechanical engineers, and a lot of students. We engage students. Uh, in fact, pretty much never high school students. I mean, there's been one or two exceptions in the 25 years we've been doing this, but college students definitely. So if you go to college, you're still interested in this kind of work, we could stay in touch. You know how to reach me. I mean,
Well, about half of our interns are in college now, so
all right, great. You see,
we're
so
getting there.
and what we try to do is find a research project that is not going to be a complete distraction from your schoolwork. I mean, ideally, it somehow fits with whatever, you know, term project you might be working on with your advisor in your college, or something that connects, you know, well with what you're studying. And then, you know, we go up to the Arctic together in the summer. So it's still pretty selective. I mean, we can't take as many people as we'd like, and we can't take everybody. But it's definitely an opportunity. So the way, and of course I'm not the only one doing this kind of work either. So there are other scientists who are doing this. But if you're interested in, for example, joining us on a field trip, either, you know, to Oregon or even the Mojave Desert, right here in California, just send me an email, and then I'll send me an email and tell me what you're interested in, and then I'll keep you posted on opportunities.
That would be
Incredible.
super. That would be really great. And then we had a question from Ankita. Could there be alien life that is just not transparent to visible light? I guess she means that you couldn't, you know, that is going to radiate in some other wavelength that you wouldn't be able to see it when you were looking.
Yeah, I mean, you know, conceivably there are all kinds of life that don't use sunlight, for example. I mean, you know, on Earth, the life forms that we're familiar with near the surface of the Earth usually take advantage of sunlight. But as soon as you go into a cave already, you will find life forms that, in fact, don't need sunlight at all. They eat the rocks. They eat the weathered products of the rock. That's how they get their energy from, and then they have water from the ground. And but they're visible still. Of course, we can shine a light on them, and then we see them. If you meant life forms that don't get exposed to light because of where they live, yeah, I think that's very conceivable. If you meant life forms that we couldn't even see just because they're either so small or invisible, that's very unlikely, because we don't just use visible light to look at them. We use ultraviolet light, we use infrared light, we use all kinds of forms of light to identify life forms, so to see them. So if they weren't visible at all, then they maybe they're just too small. That's a possibility. Yeah.
There was a headline, I think today, that I just read that a kind of bacteria that they've proven could live on Mars for 230 million years and still be alive.
Yeah.
And
Yeah. Some bacteria live for a very long time, but they have to be protected from radiation, because even if you are a very hardy bacteria, you know, type of microbe, but you're somehow exposed to just radiation on the surface of Mars, that can't be good for you. There's just no way. So for you to survive billions of years on Mars, you'd have to be underground somehow. That's conceivable. But even billions, that would be hard, because now you're talking about being vulnerable to radioactivity that's in the ground. You know, we live in a radioactive universe. Even shielded from space radiation, you still have radioactivity from rocks, and it's a statistical thing. The longer you're exposed to things, the more likely you get hit. even in our world today, you know, we are exposed to radiation every day. I mean, you eat a banana, you are exposed to radiation because bananas contain potassium. Potassium is radioactive. Some of it is. So, of course, the dose is minor. It's negligible. Don't stop eating bananas for this reason. But you stay exposed to a banana for 1 billion or 2 billion years, you will get irradiated. Okay, so that's
Over the course of a lifetime, or within a certain number, certain time period?
well, it's you know, it's cumulative radiation. So and it's a statistical thing. So if you're exposed to a lot of bananas, I mean, this is a silly example because bananas
You're
will
making
last
our students afraid of bananas.
bananas don't last billions of years, but if they could, you would be exposed to, you know, eventually you would get zapped by your bananas. Is the point.
Oh, well, that seems like a good place to end our discussion for this evening.
I can see myself being quoted for having said that, and the whole thing being.
So I just want to thank you so much for joining us. I think everybody really loved your talk. I know I did. And this is a great way to start off our new monthly meeting.
Thank you, everybody, and congratulations to all of you for being part of this program. I hope you realize it's a really cool thing to be part of.
Well, thanks for saying that. We're certainly, Ariana and I are certainly enjoying it. And we're
Thanks
happy
for coming.
Get to know everybody a little bit better, and hopefully everyone will come back next month to hear my old friend Phil Plait, the bad astronomer, talk to us about crashing things into asteroids, or asteroids crashing into the Earth, or both of those things probably.
Yep. Very good.
So
Thank you, everybody.
Thanks, everybody. We'll see you next month, November 30th. You'll be hearing from us before then.
Okay, and see you, Luke. Talk to you later.
Bye-bye.